Greetings from College Park, Maryland. In this video abstract, I will talk about restricted partitions. More specifically, I'll talk about some known upper bounds and a new upper bound on the number of partitions of an integer into a fixed number of parts. To get started, it'll be helpful to have a few definitions in place. A partition of n is an unordered sum of n that comprises up to n positive integers. We will denote this number by Pn. For example, P3 is equal to 3, as we can express 3 as a sum of the first three positive integers in precisely three ways. A partition of n into exactly k parts is an unordered sum of n that uses exactly k positive integers. We will denote that number by Pnk. For example, P53 is equal to 2, and of course P53 represents the number of partitions of 5 into exactly 3 parts, and this is equal to 2, as we can write 5 in exactly 2 ways as a sum of first 5 positive integers, and those are 1 plus 2 plus 2 and 1 plus 1 plus 3. Finally, a partition of n into at most k parts is an unordered sum of n that uses at most k positive integers. Following the asterisk notation in Kalman 82, we will denote this number by p asterisk n comma k or p star n comma k. For example, p star 53 is equal to 5, as we can write 5 using at most 3 of the 5 positive integers between 1 and 5, and these are listed here. So now, before I proceed to the results of the work, it'll be helpful to mention two important results in the field. One of these is a celebrated asymptotic formula for Pn that was discovered by Hardy-Ramanujan-Rademacher, and it is given by this asymptotic expression here. As n gets large, Pn tends to this number. That's well known. At the same time, we're going to need an inequality on Pn, and that inequality will come from a recent result that was provided by Kane in 2006, and it is stated here in the form of a double-sided, two-sided inequality, where Pn normalized to its asymptotic value, which is this number, is bounded by two constants, one on the left and one on the right. And if we isolate Pn in this inequality and write this next inequality, then we come up with two constants that will be critical, especially the constant on the right-hand side here. See subscript 1, superscript plus will be important in our discussion. And these are two constants that are known to, that can be computed from Kane's work as 0.0036 and 5.44. Now, with these results in place, we can now proceed to stating the existing upper bounds in the field, and then we can talk about the new upper bound. So the known upper bounds, there are about 4 here. There could be some more upper bounds, but they're somewhat related and similar. And the first one is by Rieger, that really appears in Coleman's work, and it is an expression that uses n and k, as it should, obviously, because we're referring to a number with 2 parameters, that is p and k. Ender's bound is somewhat similar. And then more recently, we have 2 more bounds that were reported in 2004 in Journal of Number Theory, and these are the 2 expressions that we have here. So when we look at a list of upper bounds like this, a question comes to mind, and that is, how are these bounds related together? Is any one of these tighter than the other ones, or is there some kind of an ordering between these bounds? So this is what the next slide establishes. And it states that Rieger's 1959 bound is actually tighter than Ender's bound for K between 4 and N. And then it also establishes that America's 2014 one, the first and the second bounds stated in that work are not as tight as Ender's bound, as Ender's bound is tighter, that is to say, when K is varied between 3 and this number, which is equal to 0.42 N floor. Now, this number was obtained by a series of inequalities, and so in that regard, it is not necessarily as tight as it should be, but as you can see in the next slide, we could really visualize the exact place where the two bounds intersect. So when you look at this curve, you see that Merca's bound starts out small, and then it sort of like shoots up all the way to the middle, as this could be easily gathered from the formulas here. These are binomial kinds of functions. And then it kind of goes to 0. And Ender's bound shoots up from k equals 1 all the way up to k equals 20,000. This is, by the way, a log scale, natural log scale on this side. And then at some point in time, it crosses Merca's bound, and then it continues to increase. So this place, when we look at the actual graph, turns out to be some number that is actually beyond 10,000 towards 20,000 value towards the other side. So whereas the bound that is stated here for K, upper bound, when we multiply 0.42 by 20,000, we get 8,400, and that happens to be less than 10,000. So the actual place where the two bounds intersect is greater than what the upper bound on K would suggest, and that only tells us that the inequality here on this side is somewhat conservative, that UA, that is the Ender's upper bound, continues to be less than Merca's upper bound when K exceeds 0.42 N, and that is actually sort of supported by this graph itself. But this result stands on its own, that is this result, and for K definitely less than or equal to 0.42 N, the inequality remains in effect. Now, similar bounds can be compared graphically in a similar way, but before we do that, or in fact rather than do that, we would probably be better off at this point in time to look at the new upper bound. So the new upper bound is, as you can see here, it has the same structure as the asymptotic bound for Pn, except for this constant here, and the fact that N, that would be in the original Hardy-Ramanujan-Rademacher's bound, has been replaced by N minus K. A proof of this statement is given in the paper, so I will not dwell upon that, but I will simply state in the next three results here that the new bound is less than all of the bounds that have been cited prior to this slide, and this has been established in the paper mathematically. More specifically, when K is between square root of N, order of complexity wise, and log N, and N minus that same number, which keeps K very close to N, the new bound is less than or equal to Merca's first bound as well as the second bound. When K is between square root of N plus some log N term, which is obviously smaller in order of complexity than square root of N, and all the way up to N, this new upper bound also remains smaller than Ender's upper bound. And likewise, for a very similar set of values for K, another square root of N term here, all the way up to N, the new bound remains less than or equal to Rieger's bound. Now, to really get a feel as to how small, that is, the inequalities are there, but how small U nu is, the new upper bound is, we can take a look at this graph, and that kind of shows you how these existing bounds compare against the new upper bound, or the new upper bound compares against them. So the red one is the new upper bound, which seems to hug the k-axis here, and the other bounds, the Rieger and the Andrew bounds, shoot up all the way up to k equals 10,000. Again, this is in natural log scale on this side. And the Merca's bounds start, this is, I guess, the first bound, but the second one is very similar, starts fairly small and then shoots up and then goes to 1 again. But in between, it's much fatter and much larger than the new upper bound. So this is perhaps the main result of the research that I conducted. The new upper bound is significantly smaller than all the other upper bounds that have been reported. Now, we could also look at the new upper bound against or versus the exact values of P and K to get an idea as to how it really compares with the exact value. So this next slide sort of suggests this. And I look at values of K between 1 and 1,000. I picked this number to be somewhat smaller than 10,000 because it's a little harder to generate these exact values because they grow exponentially, as in fact the asymptotic formula would suggest. But even for this particular domain of values of K, you can see that this red curve, which is the exact values, which depicts the exact values of P and K, is closely followed by these two other curves, especially this one, the black curve, and then the dash curve, dash line here, or the dash curve. And so, especially when K is beyond 100, all the way up to 1,000, it seems like the black one hugs this red curve, which is the exact set of values of P and K when K ranges between 1 and 1,000, which is the value of N. Now, so let me just mention that the black curve here is, in fact, the asymptotic formula with N replaced by N minus K. And in that regard, we cannot really view that as an upper bound. And nonetheless, you can see that that asymptotic formula with, let me just go back here for a second, with N replaced by N minus K here, gives us a curve that is basically hugging the exact values of P and K. And the other curve is a proper upper bound because we use in this case the upper bound coefficient in Keynes' work, and that gives us, by way of this new result that I mentioned here, a proper upper bound. Both of these curves, as you can see, track when, of course, the asymptotic one more closely. So then the one with the Keynes upper coefficient, the exact values. However, as we said already, the one with the Keynes upper bound coefficient gives us a proper upper bound, whereas the other one is asymptotic somehow, and it cannot really be claimed to be an upper bound, even though in this curve it clearly is following from above the exact values of the P and K. Now, the next slide shows us a similar sort of graph for P star and K, which is the number of partitions of N into at most K parts. And results are similar, except that the gap widens because of the way that P star and K is formed by simply adding P and K terms together. And so that ends up basically causing this gap, more so for the upper bound with Keynes' upper bound coefficient than with the asymptotic value. But it sort of suggests again that for K exceeding a certain small number here, somewhere in between 1 and 200, the curves sort of like become close together. So with this, a few problems remain. Two problems especially are worth mentioning. One would be to derive a tight lower bound for P and K and P star and K. And then the second one is really to prove if this is not the case. If we cannot come up with a tight lower bound, that this upper bound is somewhat tight, at least for P and K, and then maybe try to proceed to obtain tighter upper bound for P star and K. For a tighter lower bound, let me just mention that the known lower bound for P and K is n minus 1 choose k minus 1 divided by k factorial, which is not written here. And that comes from the counting of the number of compositions of n into k parts, which is that formula n minus 1 choose k minus 1. And then when you divide that by k factorial, then you get a lower bound on P and K. Now that doesn't seem to be too tight for the entire range of values of k. And so one result that probably needs to be improved would be to bring that lower bound to some number, some formula which is in this vicinity here. And this second statement here is basically to show that this is tight so that the lower bound is not too far from this. So basically these two problems are coupled together and would suggest that there's some more work to be done. But this brings me to the end of this presentation. I hope you enjoyed it. And I also hope that you get to read my paper when it gets published in Journal of Number Theory in one of the forthcoming issues. Thank you.